Okay, then let's welcome next speaker, Gunther Vollrath from Aifotec.
Okay. So, yes, maybe. Okay, so first of all, thanks for the invitation, for having a talk here at the conference. I will talk a little bit more on the 30,000 feet view of the industry. Unfortunately, I'm not allowed to give any details of what we are doing because all the designs are for sure customer confidential. But I will talk a little bit about the markets, so where the volumes are, price targets, assembly costs, and so on. So, who we are. That's our fab located in the middle of Germany, right in the middle of Germany. So we are running several systems here. You see there's a typical Aifotec production cell. We are also using other suppliers. So we are not doing any assembly tools. We are only using these tools, but we are developing processes and we are doing volume manufacturing of these. So what we are, who we are, so we are a pure play contract manufacturer. So you will never find an Aifotec product out there in the market, although we've so far produced several millions of units. We're based in Germany, as I said, 15 years in business. 80% of our customers are located in the US. Privately owned, profitable, so everything is running fine. What we are providing here, it's the OE service, process development, design for manufacturability, and sample production. That's especially for the big players in the market, like let's name Intel or Cisco. They already have set up their production line somewhere in Asia. So for these guys, we are usually doing the process development only. However, we are also doing assembly tool consultancy service. And for smaller companies, we are also doing the FAT, SAT, pilot run optimization. For example, let's name Intel. They ship back machines from Thailand back to us to optimize these machines. So we double throughput on these machines and send them back to Thailand. Markets are datacom, automotive, medical. So far, let's say I will focus on in the presentation, I will focus on datacom. However, as Ignacio already mentioned, a big market right now is also LiDAR. So we have several LiDAR customers based on MEMS, based on classical, let's say, mechanical design. So this is really growing business in volumes. And we are doing pilot production and volume production up to, let's say, X million pieces per year. So let's say everything up to 8, 9, 10 millions. That's our business. If we are talking about 10 millions, one customer was talking about 100 million pieces per year, then we are working together with a partner or partners in Asia. It simply doesn't make sense running, I don't know, 20, 30, 40 machines in parallel. So what we do is everything around passive alignment, so image recognition based, edge-emitting lasers, arrays, VCSELs, mirrors, etc. Active alignment, mainly lenses, lens arrays, prisms, filters. So these are really actively aligned within the optical train. Assembly of micro-optical benches. So I think it was already mentioned, and I will also have a picture later on, the classical lamp look-alike micro laser, which is now used also for other applications and by other customers. So platforms we are serving, it's silicon photonics, silicon polymer, Pyrex PCB, whatever. We are using epoxy, UV epoxy and thermal conductive epoxy, and also eutectic bonding. So eutectic bonding is used by spot size laser. So spot size ranges 50 times 50 microns squared up to several hundred microns squared. And we also have a heating plate, a Aifotec heating plate system, which is used for large die sizes. So this is a typical application, so small dies, which is soldered by spot size, and here the larger dies are usually soldered on a heating plate because you simply cannot use a laser and have this large spot size. As I said, volumes ranging from dozens, so dozens was a defense application, usually space. This is only, let's say, 50, 60, 70 samples. And datacom, it's more the million range. And accuracy we are providing, it's down to 0.5 micron by passive alignment. 0.5 micron passive alignment, it's not into production now. It's still in development, but we have several customers requesting this accuracy. So 0.5 micron accuracy by flip chip bonding. So flip chip bonding of laser arrays in front of waveguides. So, assembly yesterday, today, and future. Yesterday. I like this one here. Who understands German? So, means working hard today, otherwise you will look hard for a job tomorrow. But this is a typical, let's say, 20-year-old Asian manufacturing. Now it looks more like this. That's our lab. You see you have these assembly machines, sometimes one machine used for lenses, other used for isolator, other used for lasers. These are individual machines, so these are all wafer level based, so there's no need to use a conveyor belt because population of one wafer takes, I don't know, 1 to 2 days anyway. The future, what people are requesting us, it's, so hope I can start the video. That's actually a customer entering our lab telling us these machines are much too slow. I would like to have something like this. You see, it's like a Gatling gun. So it's picking up the components and shooting these chips onto a PCB board. So it's called a chip shooter. It's a Fuji chip shooter. You see, it's really difficult for the human eye to follow what's going on, and that's it. So customers, especially out of the electronics or automotive world, they are showing up asking me, Gunther, your machines are way too slow. I need a much faster machine. So take a look at the total available market of assembly tools. This is 20 million. It's a worldwide data market for 100G modules. Worldwide, all customers. This particular customer was a LiDAR customer asking for 100 million pieces. So there's simple mathematics. You know, you have 4 assemblies per device in this case. For example, you have a laser, you have a lens, you have a mirror, a turning mirror, and for the LiDAR system you also have 4 components, means this number of assemblies. And if you have assembly time of 30 seconds, which is standard right now, or you have 1 second, or you have something like a chip shooter, like 0.1 seconds, it will end up with these tools, total available market for these tools. So everybody can see, I think this is a reasonable number. This is probably not an interesting business for the tool manufacturer, selling only 3 machines, and this is complete nonsense. Because these guys, they told me, Gunther, there's no problem, we will not work together with one of these German companies, they are way too slow, we will go to Japan or Korea and they will build us a machine. So they will build us a machine, this one, 0.1 second for optical assemblies. So I told them, good luck, we will see again. We saw again, they bought a Aifotec machine. I told them, one of the Korean or Japanese, or let's say Fuji as an example, the chip shooter, no company will develop a special machine, special machine for doing assembly of one piece part, special design for a LiDAR system, and selling one tool. So they can sell, so one tool in production and maybe one running 30% only. Or at least they will charge you, I don't know, 20 million for the tool. So as I said, the total available market for these, what is requested by the customer, the volumes are still not there in photonics. Even if you're talking about here high volume automotive market. So assembly technologies, it's usually difficult to, really have to educate the customer why we are not running 0.1 seconds with optical assembly. So these are some reasons. It took me weeks to convince them, but finally I think I made it. And as I said, they bought a Aifotec machine. We have very high precision here in optics. So as I said, we are talking about 0.5 micron or even below. We have a brittle material. You cannot compare it with shooting SMD components on a PCB. So you need to handle this material very carefully. It's pressure sensitive. So usually we are using a pressure, for sure depends on the size of the die, but usually, let's say, tens of grams for a laser die, for example. People are requesting, I would like to have thermal compression bonding, and I need, I don't know, a few hundred grams. Even if the chip will not break, you will introduce dislocations here, which will affect the long-term stability. So this material needs to be handled very carefully. Then you have non-touchable areas. For example, a laser ridge, you're not allowed to touch the ridge for sure. You have a PD aperture, you are not allowed to touch. You have lenses, prisms with optical coatings. So it's a complete different world compared with electronics manufacturing. And for sure, we have a gel pack, blue tape, or waffle pack. So there is no such thing like putting a reel of laser diodes into bare die laser diodes into the machine. So that was something I told the customer. It's no problem if you will find a customer. If you will find a supplier who will supply you with bare laser diodes on a reel, we will build you such a fast machine together with a partner. For sure, they never managed. They are still shipping on gel pack or waffle pack. So what we are doing at Aifotec, an overview of basic assembly technologies. We are doing image recognition-based alignment, so which means that the device is not operated, which is mandatory if you're doing flip chip. For sure, if you're doing flip chip, you don't have access to the contacts anymore. So this needs to be done by image recognition only. And as I said, here we are working on 0.5 micron accuracy, which is so far not in production. We are using passive alignment, so edge structures like inverted pyramids for lenses, etc. I will show you a picture as an example later on. We are not using passive alignment by solder adhesion. So there was a big hype maybe 15 years ago about using standoffs and alignment marks and to passively align chips with respect to solder pads. As far as I know, nobody is using this in the optical industry, at least not for volumes. It's a nice academic work, but it never made it into production. We are not doing any blind search. So when doing active alignment, usually it's some sort of hybrid alignment. So we're doing a passive pre-alignment, so we already have light, and then we are doing an uphill search only. As you mentioned, there's a very sophisticated algorithm, and if you already have light, active alignment could be pretty fast. So the old statement, active alignment, needs lots of time, and it's very slow. This only holds if you really start with a blind search. If you have first light, it's pretty fast. We are not doing any photonics wire bonding. There are other companies evaluating these type of technologies, like Vanguard or multiphoton optics, and we are not doing heterogeneous integration. So Intel is not really heterogeneous, it's more a wafer level assembly process, or Scorpios, they are really growing the 3.5 material, or trying to grow the 3.5 material onto the silicon. So some statements for photonics assembly. First of all, we are trying to buy a machine, and you have a data sheet showing 537 micron precision and 3 sigma, and let's say single-digit seconds for the machine. It will not work. You can achieve below 1 micron, but it's really difficult to achieve it at 3 sigma. You can build a fast machine, but you will use accuracy. So you have to choose your poison here. So don't believe this is possible doing all these 3 specifications in parallel. So if you have a fast machine, you will lose accuracy. There's no way around. You can have multiple, let's say, heads. That's also something we've done and we've optimized. Oh, we haven't built the machine, we've optimized the machine. But you are moving around large masses, and you will not achieve this accuracy. High precision. Usually these machines are specified with a glass master. So 0.5 micron with a glass master, okay. Repeatability, fine. 3 sigma, fine with a glass master. What we are using here in an industrial environment, we have a combination. So we need very good materials. So we have the platform, let's say a silicon wafer. Silicon wafer is never perfect. So you have alignment marks, which are sometimes good, sometimes bad. You have laser diodes. Sometimes you have an overspray, we call it overspray, so the anti-reflection coating covers the edge of the laser, which will affect the image recognition. And you need highly skilled workforce. So still running such a machine, it's not having an operator simply sitting in front of this machine, and it's still, as I said, below 1 micron. It's still a combination of the machine and the engineer to develop such a process. So I usually compare it with Formula 1 drive. You can have the best driver and a bad car, and you will not win. Or you can have the best car and a bad driver, and you will not win. But achieving this type of accuracy, it's really challenging. Okay, take a look at the market. Where are the volumes? And yeah, maybe silicon photonics, it's a sweet spot here. So first of all, let's take a look at what's going on in the internet. I think it's a well-known slide. Interesting thing here is we have approximately, it's 2 years old, I think, so it's a little bit more now, 640 gigabyte of global internet data transferred. So do we really need faster internet? And by the way, 70% of the traffic is inside the data center, so it's not long range, but do we really need faster internet? So this is a very interesting slide presented at the IEEE conference in Santa Fe. So this gentleman, So this gentleman was located in Melbourne, or this institute is located in Melbourne, and he calculated how much it will take to transfer 100 terabyte, which is approximately 2 hours of data load of the internet, copy everything on a USB stick. So you have these 33 gigabyte USB drives, put it in a post box, send it by cargo jet to Santa Fe. So it will take 100 tons CO2 equivalent, and it will take 24 hours and 10 to the minus 10 grams CO2 equivalent per bit. Very interesting. If you transfer the data by internet, let's say 100 gigabit line, it will take 10 times CO2. It will take 2 months. I think that's very interesting why the whole internet, or why people are still looking into higher speeds and especially lower power consumption. So the power consumption of the internet, the data center and the data transmission, it's amazing. They have calculated it in a nuclear power plants equivalent, and I think it was 3 or 4 nuclear power plants per year you need to add only because of the internet. So that's why people are still working on new devices, new components, and the growth of the industry. It's not only driven by new data center. For example, Microsoft, they call it crop rotation of all components within the data center every 2 years. So every 2 years, all components will be replaced by new components, not because of the speed, it's only because of the power dissipation. So they can save so much money because of the cooling. 50% of the power dissipation of the data center approximately is cooling. And so they're doing this crop rotation every 2 months, every 2 years, which is really driving the business. And very interesting, now you see the speed here. So in the good old days, the telecom client side was driving the speed. Right now, the hyperscale is overtaking. So the hyperscale computing is really driving the market. So typical look inside the data center. You see that's a Microsoft data center, and they are replacing all components inside these containers every 2 years. Same for Google. This is Google. This is Google. I don't know what this is. But these data centers are really now driving the market, silicon photonics market. Well, that's one of the forecasts you will find. Rapidly growing market, very interesting for sure for doing assembly in volumes. So take a look at the supply chain. That's a Yole development study, so it's not mine. You have the manufacturers here, like a Aifotec, so the suppliers, the wafers, manufacturing equipment, materials. You have the chip firms here, which I'm a little bit proud of because I didn't put Aifotec in here, it was Yole. So we have the let's say, service suppliers here, and we have the optical interconnect firms, servers, and the end users. And very interesting what's going on right now. The end users, like a Google or Facebook or Amazon, Microsoft, they are moving into this market. Also Cisco, everybody probably knows, has bought Luxtera. So that's also, again, an old Yole development slide, 2012. And the red lines are added. I have added the red lines here. So this was going on in the industry right now. So there are some companies, the fabless sold to Huawei, Orion is called to a system provider, Verizon. There are new kids on the block, like Sequoia from Germany, Avago is sold to Foxconn. Couture is sold to Mellanox, and Mellanox closed down the business. This could also happen. Then we have Couture was sold to Rockley, and Luxtera. I think that's the biggest success story in the industry. They sold the active optical cable business to AOC, and just sold the remaining business to Cisco for 660, 680 millions of dollars. So there are still merger and acquisitions going on. However, always please keep in mind, so the typical hype cycle general, so we are still here somewhere, the technology trigger. So we are, the mass media hype begins with the data center, cloud computing, etc. We have still not reached this slope. So somewhere here the business is going on. LiDAR, maybe it's even more in this range. So there's lots of hype in the newspapers. Everybody is talking about autonomous driving. In Texas, I think it was in Texas, first people start shooting at autonomous driving cars. So there's still several open questions with this type of technology. But anyway, okay, where we are. Just to give you an example, as I said, usually I'm not allowed to give any examples how an assembly will look like. This is public, so that's why I'm allowed to show these. Let's say AOC example. You see, it's an old one. Right now they are at 100 gigabit per second. So the classical active optical cable. You see, there's not as much inside the cable anymore, inside the case here anymore. So this is free PCB. We only have the optical engine here. So this is the CMOS chip, and they call it LAMP. There are some other companies using different names. So the optical assembly here. For a company like Aifotec, for sure, interesting thing is building this type of optical assembly. So what's inside? We have the laser module here. We have the, as mentioned by Ignacio, the fiber assembly here, which is maybe too close. And inside this optical module, here's the laser module again, the fiber. And you see it's really very close here. And inside we have the laser, the lens, and the optical isolator. So this is typical business for Aifotec. Full wafer assembly, 3,000 components on one wafer. And let me show. How it works. So you see the, that's the, sorry. That's the laser process, which okay. You see that's picking up the laser die. So that's the laser die here. That's a silicon submount. So the machine is picking up the die, doing the alignment here, placement of the laser. The laser is bonded by the infrared laser. So the camera is closed now, and you see the laser is placed. So you're doing a post-bond measurement, and the machine goes to the next. Next side, similar. It's also for the lens placement, and then for sure you need to place the whole component on a silicon photonics wafer. So these are LAMP modules. As I said, approximately 3,000 on one wafer, and then the machine is placing these lamps. You see the element here, die contamination check, and placing on the silicon photonics die. You see the tilt control, because it needs to be perfectly in parallel for sure. So electrical test. And then it's epoxy bonded on the silicon photonics wafer. You see the active alignment, as Ignacio said, it could be pretty fast. And then you are doing the laser adhesive cure. Okay, some price targets. We are talking here for sure not about thousands of devices. So the market is looking into millions. That's where we are right now. So here these micro optical cables. So this is an old data I presented in Berlin 4 years ago. And we were talking about a card-to-card $1 per gigabit. At this particular conference, people said, Gunther, this will never ever happen. You know, $1 per gigabit, this will not happen. We are right now in the range of, let's say, a few gigabit per second. And next target is 0.5 gigabit per second. Actual request we have, it's 25 seconds per gigabit. For sure, this is for very high volume assemblies. So what does it mean for the assembly? Assembly costs 80%. From our point of view, if you take a look at the gigabit per second and the dollar per gigabit per second, I was putting in $3 here, which is pretty much conservative. You have the cable costs, you have, let's say, 50% production costs and 50% costs of the optical engine. And if you're using a 4-channel module, so if you really have 4 lasers, 4 lenses, 4 optical isolators, 4 lamp placement, and so on, you will end up with 34 assembly steps. Usually in this range, you'll have less steps. But let's say 34 steps, you will end up with as optical assembly module cost 55% down to 11, and the assembly of the full module, so assembly cost for the full module, goes down to 3%. Same analysis for 10. For example, if you're using only 1 laser source, which is like they were doing, 1 laser source, splitting this source into several lanes, you will end up in the range of, let's say, a percentage, 1% assembly cost full module, or 30% of the engine projected to 2024. So assembly costs are rapidly going down. And last slide, assembly cost comparison. For sure, everybody's talking about, or was talking about, let's go to China and Thailand. It's much cheaper than doing assembly in Germany or in Europe. These are, I haven't updated this. Right now we are, I think, at €9 something minimum salary. But if you take a look at these minimum salary costs and the assembly tool costs, fully automated depreciation, etc., and yeah, there's no rocket science here, and you assume 100% manual assistance on the machine, or 10%, and you're paying a salary minimum or 2 times the salary minimum, you end up the red curve, red numbers here are within a 10% plus. So you see, at 10%, we can easily produce in Germany or the US. Here it's also in plus 10% range, and also keep an eye on the actual of the assembly costs here, if you can do 2 seconds or 30 seconds. So the difference here is in the 1 cent range only. Okay, so thank you for your attention. Any questions?
Thank you, Gunther. Okay, questions? I feel curious myself when you brought that case at the very beginning of the talk with this customer willing to reduce the time for all this assembly. Is this just the will of the customer, or is it just a pull from the market that they need to deliver so many devices per year?
Yeah, first of all, they need to deliver lots of devices, so the high volume. And yeah, they are simply not willing to buy, let's say, 100 machines. And for sure, especially for this type of market, there's high pressure on the LiDAR system, for example. You know, right now, a LiDAR system is in the range of, I don't know, 20,000, 30,000. There was a new LiDAR at the CES, a short-range LiDAR, low-cost LiDAR, which, by the way, was built at Aifotec. But so for the automotive industry, you really need to achieve a few dollars per LiDAR system. Let's say 10, maybe. You know, so you really need to bring the cost down from 20,000 down to right now, let's say 1,000 maybe, but you need to show a path towards a few dollars per assembly only. And they simply cannot achieve, especially they're trying to ramp up the market as fast. For these type of volumes, by the way, I think it will take some time before they will sell 100 million of pieces. But it's simply not doable. You know, if I show up at Aifotec, Ignacio and Thorsten, asking them, guys, I need 200 machines for a customer, you know, in 6 months. It will not happen, you know. You'll probably not. you need to buy. You need to buy the cameras. You need to buy the stages and everything. So it's not the bottleneck. It's not only Aifotec. It's the whole industry. And for sure, you know, these guys, they are not the only tool manufacturers, but none of these guys is really interested in having such a fast machine. As I said, they can only sell 2 worldwide market. You know, there's no business case behind. So they're still, for me, as I'm only using these type of machines, for me, there are still some, let's say, unwillingness to build really fast machines. Okay. You know, why should I speed up, I don't know, 10 times? Why? You know, I will pay for a machine which is, let's say, 5 times faster. I'm willing to pay twice the price as a user of this machine. So.
Okay, thank you. Oh, question here.
So thank you for your presentation. It has been very encouraging to see that there is future for Europe in assembly. You are exposed to many markets in optics and photonics, and you have mentioned that the volumes now are in silicon photonics, for example, with transceivers in data centers and LiDAR systems. But do you see or you foresee in the near future any other market taking up in significant volumes?
That's a good question. Well, for sure, I cannot comment on forecasts and the real world. Usually, these people, especially as 80% of our customers are located in the West Coast, the markets are still not there. For example, as I said, 100 gig modules, the worldwide market, it's 30 million. So people were talking about, I don't know, one customer was talking about they want to sell 10 million on their own, so 50% market share worldwide. You know, for sure, this never happened. Same with the automotive guys. You know, they came down from 100 million to, I don't know, 1 million. Right now, we are talking, for this year, we are talking about 10K. So the, let's say, expectations are, there are still people that are still talking about these large numbers, and yeah, they showed up with large manufacturing plants, dark factories, you know, fully automated, somewhere in Asia. So they asked me who can really build these large volumes. As I said, 10K, that's a real world for this year. So coming down from 100 million. So that's the experience. We are usually, every customer showing up with a forecast, I usually divide it by 10. And usually it's even lower. So the market is still not there. The high volume market, let's say really hundreds of millions for silicon photonics. Could change with maybe medical applications. We also have customers working in medical. This could be disposable, whatever, implants for blood sugar sensing. Could be a huge market. You know, 50% of the population of the US needs such a sensor, maybe. But then you have the federal the drug administration, so it will really take long entering this market before you can really shoot a small silicon photonic chip into the body, control blood sugar by smartphone, etc. So it could be a huge market, but will take definitely some more years. So these curves, the level of expectation curve, you know, as I said, we are still, all these industries, silicon photonics, we are still on the, let's say, ramp up side. So we will see a decline, definitely. That's my point of view onto the industry and it's for the last, let's say, 20 years. So usually the real world, it's much different from the market marketing guys what they are promising here.
Okay, thank you, Gunther. Thank you.